silly. Okay, science time. You're getting me all off my axis. I'm going to, my sickle moon soul is going to vibrate off its axis here if we're not careful. Science time, as I said. Today, let's give this a title first, and then we'll move on to the next thing. I was going to do red, but I'm going to see how it shows up on the video. We're going to call this thermochemistry. Let's call it actually thermodynamics, because that's actually what I want to call it. Thermochemistry is what my Chem 2 class is currently working on. They're going to take their test today, but we're going to call this thermodynamics. And as you can see, the objective written here and on the Promethean, and I'm going to say it out loud, is, and you should write in your notes, describe stability and change in the context of thermodynamics. Stop it, doll. You're making me cough. Why do you think I chose specifically those words for the objective, if you had to guess? I'm sorry, Whitley, what did you say? Thermodynamics? No, not that word. Why do you think we use the phrase stability and change, or that little noun phrase, stability and change? Hopefully that reminds you of something.
The last chapter.
No.
The chapter before the last chapter.
No. They're on a poster in here.
Oh, it reminds me of up there.
Yeah, it's one of the cross-cutting concepts. You get a Ramrock. Walden, you get one for pointing at it, because you knew what I was talking about the whole time. And anyway, the reason I've chosen that is because that cross-cutting concept that applies to all science, and really all of life, is the one we're going to focus on for this chapter. And I'm going to try to do a little bit better job of including those in the objectives, because in my opinion, that's one of the places that they could belong. So you may have noticed in the last chapter, which was about work in simple machines, we said it was, or something like, describe cause and effect as they relate to simple machines, and that's one of them too. So I'm going to try to do a better job of including those. All of them apply all of the time. We could think of, do you think that the cross-cutting concept of energy and matter applies to thermodynamics? Let me ask you again. Do you think that the cross-cutting concept of energy and matter applies to thermodynamics?
Yes.
Yeah, of course it does. Because, well, give me an example of energy and matter in just your lab. What was an energy source in your lab? The hot plate. Yeah. What was the main matter that you were concerned with in your lab? The water. Yeah. So that applies. Could you say that scale, proportion, and quantity apply to your lab? Yeah. If you used, instead of 200 milliliters, if you used 20,000 liters, would that have made a difference in the effect of your lab? Yeah, that's a different scale. Of course it would. Anyway, so we're talking about thermodynamics, and I want to start by asking someone what the response they had to their bell work was. Does someone want to volunteer? If not, I can do the spinner. Someone want to volunteer to share their bell work? I'll choose Hunter this time, and then we'll probably have Kesslin and Whitley choose theirs too.
Mine is kind of little.
Why don't you describe it to me and I can draw it? What did you draw?
So I have 3 beakers.
You drew 3 beakers to begin with, and you drew them like this, right?
Yeah.
Let me give you a little side note here, because I love giving side notes because it distracts you. Sometimes when people think about science, and they're doing like science clip art, and I bet even if you type in science beaker, into the Google image search and find some clip art, it's probably this. You know this little guy, and it's probably smoking. You know this guy. This is not a beaker. This is an Erlenmeyer flask, and people get that wrong all the time. This is a beaker. Why do you think this is called a beaker?
Because it has a beak.
Yeah, him has a little beak. This does not. They do make such a thing as a fleeker, which is a flask that also has a beak, and they call that a fleeker, which I hate.
I love that.
And then you probably drew that there was some liquid in these. How did you indicate that there was liquid in these?
I did a little line.
You drew a little line about
That's
there.
really low, but
Well, I'm going to just put it there. And then what did you draw within the little lines? Or
dots, and then I got arrows, but on that one, that's a slow moving one. So
Okay.
I'm going to do a tiny dot, long arrow, tiny dot. Because they're slow.
Okay. So in yours, you used long arrows to indicate slowness because it takes them a long time to get that distance. I'm going to use short arrows to indicate that because I'm thinking about it in physics. Usually we indicate the velocity of something with an arrow, and the longer the arrow, the higher the velocity. So I'm going to use short arrows, but I see where you were coming from, and there's no right or wrong way to do this.
Okay.
I'm just going to use short ones because that's kind of the physics convention. Okay, and then in this one,
And then I labeled it cold water.
Cold.
Moving particles.
okay, let's just put cold for now. And then you put,
You got room temp.
yep, and these ones are,
Normal. They're just like.
yeah, so slightly longer. I accidentally drew that first particle bigger. I did not mean to do that. That's not
I
the,
did that too, Mr. Kime.
me and Gunnar are the same. in that very one specific way.
And then I just put room temp.
Okay.
And then on hot water, they're like super fast, and like I put the arrows through them, or like kind of them. They're just crossing over each other.
Thank you, Hunter. I like that description. They're doing crazy stuff, and this is called
said the particles move faster in hot water.
hot. This is hot. And the particles, as we said, are moving faster. They're moving fastest here, and they're moving slowest here. And then what was the result of your lab? When you came and dropped in your what looked like purple food coloring but turned out to be orange, when you dropped that in here, what was the effect? After let's say that I'm drawing this after 1 second of dye. 1 second of dye. What did this one look like compared to the other ones?
It was really slow.
Yeah, less spread out. This one was maybe a little bit more spread out, and this one was probably really quite a lot spread out. Why?
Because the particles move faster.
Exactly. So what this lab was supposed to have demonstrated to you, and we'll hear from a couple other people here to verify this, but what this lab was supposed to have demonstrated to you is that we can view the differences in particle motion. We can think about particle motion as with the proxy of how far the dye spreads. Think of it this way. The water is like a little pony in your cowboy game, and the dye is like the little cowboy. And the dye is going to ride on the pony to get to wherever he's going to go. And the faster the horse is moving, the faster he gets to where he's going. So in the cold, slow-moving water, the pony doesn't carry him as far. And in the fast-moving hot water, the pony carries him farther. So the dye is able to spread out more. And that's a really simplistic analogy that I would probably tell to a kindergartner, but that's some of you. So no, I'm just kidding. None of you is actually in kindergarten. You've nominally met the requirements to progress to 9th grade somehow. So, okay, does this kind of make sense though? Let's hear someone. Kesslin, did you write a description?
I wrote a description.
Yes, I know, and I appreciate that. I just want to hear someone else's. Thank you. You did a drawing too. Did anyone write instead of drawing? You all thought it would be easier to draw?
Yeah. And it's more fun.
Yeah. You might enjoy the class that I teach called Earth Science, because on every Earth Science test, instead of math problems on the back page, which you do, the back page is all concept sketches that you're supposed to draw, and then good. Well, please do. No one wrote a description.
Nope.
Let's write a description as a group. I said I was going to write with red, and here I've literally written one word with red. It was a long word though. Here we're going to do brown. Let's write the little description. I'm going to start this way. In cold moving, what? No. In cold water, the particles, what? Fill in the rest. Someone raise your hand and then fill in the rest. In cold water, the particles will move more slowly and they tend to be closer together. This we're going to get into when we talk about solids, liquids, and gases in chapter 18, maybe. I can't remember. No, it's not chapter 18. Might be 16. But when we get into this, we'll find out that in liquids this is not really true, but we're going to put it anyway because it does tend to be true with matter in general. In cold water, the particles move more slowly and are closer together. Semicolon. I'm going to skip the room temperature because you can assume, if I say this about cold water and I say another thing about hot water, what can we assume about room temperature? Yeah, kind of in between. So in cold water, the particles move more slowly and are closer together. Or someone raise your hand for the next part. I want you to say the whole thing. I have a semicolon here, so I'm going to put another sentence. Kimber.
In hot water, the particles.
In hot water.
Particles move faster and are more spread
And are more spread
out.
out. Good. Why did he write that? Do you think there are circumstances in which this may be subverted? That is, do you think there are circumstances in which, for whatever reason, cold water are either closer together or moving faster than in hot water? Do you think that might be the case sometimes? Sure, yeah, it might be. So I'm going to put in general. This is true in general of matter, but it's not necessarily true in every single case. Let's talk about 3 vocab words here. And the reason we normally don't bring up vocab words in the discussion, I mean, we use the vocab words, but we normally don't define vocab words all that often in the discussion, but I wanted to find these ones for you or with you so that you have an understanding of the differences. They are thermal energy. This should ring a bell. Does it? Does this ring your bell?
Yeah.
Heat
That rings my bell.
and temperature. Temperature. All of these are the same thing, yes or no? No. All of these are related, yes or no? Yes. Thermal energy, heat, and temperature are related, but they're not the same thing. Thermal energy, shh, please calm down. Thermal energy, you should remember this from chapter 5. Thermal energy is what? Good.
Thermal energy is energy from the sun.
No, not necessarily.
Heat energy.
Let's be a little bit more. What? I'm looking for the answer to what is thermal energy. Yeah, okay, good. It's sum of kinetic and potential energy in particles. You can make the case that this is true on macroscopic objects, people, tires, apples. You can make the case that's true, but we really only talk about thermal energy in the term of particles. It's the sum of the kinetic energy. Remind me, what does kinetic energy have to do with? What physical property does kinetic energy have to do with? The energy of something has because of its... No. Well, not no, but that's not the best thing. Motion. Motion. And potential energy is the energy a particle has because of its... No. No. No, this is potential energy. Position. Remember we talked about gravitational potential energy? These objects, my beautiful new sailboat, which you probably can't see on screen, has gravitational potential energy because why? Because it's up high. Because there it is. Because where it is, right? A bowstring, for a bow, you're actually supposed to pull it this way. A bowstring in a bow has elastic potential energy because of where it is. These particles have potential energy because of where they are, but in this case, how they relate to each other, what they are, how close together or far apart they are is potential energy. These things are potential energy. And let me erase this and make it green so we can keep it straight.
So Christmas.
Ooh, Christmas. And the kinetic energy that the particles have is probably due to their motion, but which part of this phrase is that?
Their speed.
Yeah, so which part of this phrase is that? Move more slowly and move faster. These ones are the kinetic energy that they have. So this phrase is describing what? As we just defined it. This phrase, in cold water, the particles move more slowly and are closer together. In hot water, the particles move faster and are spread out. That's describing the what of the systems. I'm pointing at it. Thermal energy. The thermal energy. So the thermal energy is the sum of the potential energy, the potential energy, how far apart they are, and the kinetic energy, how fast they're moving in particles. What's heat, then?
Thermal energy doesn't go through something at a higher temperature.
Okay, wait, you said the exact right word. It's the what? There's the verb in that phrase was flows. Yeah, the flow of thermal energy. Say it a different way. Good, yeah. No, don't say that.
The wolf.
No. That's funny, though, Gunnar. That is really funny, but I'm not going to accept that. The flow of thermal energy, but it's the movement. It's how thermal energy moves, how it transfers from one object to another. Energy transfer. Specifically, thermal energy transfer. What must this be, then? From what to what? On some level, it's from one object to another. If I... This is empty now. But if if this was hot coffee, pretend it is. There's no reason you don't think it is because you can't see what's in here on your screen. Pretend it's hot coffee, though. I could feel that it's hot, and I'm feeling heat. I'm not actually feeling thermal energy. I'm feeling the flow of thermal energy from a hotter object to a cooler object, my hand. What if I touch this? How does this feel to me?
Cold.
It feels cold. It doesn't say the flow of cold from one object to another. What's happening? What do I feel as cold?
Feeling it's thermal energy.
I'm feeling,
The loss of thermal.
yeah, exactly right, Faye. I'm feeling the thermal energy from my relatively warm hand flowing into the whiteboard. Thermal energy, the movement of thermal energy is heat. What you feel as cold is when thermal energy is flowing away from you. What you feel as hot is when thermal energy is flowing into you. You're all relatively fit people. You probably run, and you probably sometimes do that in the summertime, and you get really, really hot and sweaty. What's a good way you can cool down? Swimming. Go home. Why home? What's special about home? It's relatively cool. It's air conditioned. You can very quickly cool down by going into your basement, I guess anyone's basement, and laying on the tile floor, because the tile has high thermal conductivity. It'll quickly remove the heat. It'll quickly remove the heat from your body, and that you feel as cold. But the reason you felt hot in the first place is you had a lot of flow of thermal energy into you, so that the removal of that you feel as cold. And then what is temperature?
Temperature is the measurement.
Measure. Yeah, measurement. Underline that, please. I hope someone's writing this down. I haven't seen anyone write. This table does a great job of writing. This table does a half great, half buns job of writing, and that table is a buns job of writing. Measurement of the average, what? Kinetic energy of a substance. I'm sorry, let's not write that. Let's not write that. I don't think so. It could be, but it isn't only that. But it's a measurement. It's a measurement. It's a way of measuring thermal energy, specifically the kinetic energy part. And it's the average. In what context do you ever record a temperature? Yeah, when you're sick and your mommy comes into your room and takes your... Shh, please, let's try to once in a while sit down and also not talk so much all the time. When your mommy comes into your room and takes your temperature, do you think it's true that every single particle in your forehead, this is your forehead, I'm going to draw the zits on it even. There's all your zits. Do you think the particles that make up your forehead, which looks like a loaf of bread, do you think the particles that make up your forehead are all moving with the exact same potential and kinetic energy? No. There's an average. Just like in the same way that when I look at your test scores, I see that the class average was a 71%. Does that mean that every person in the room got a 71%? No, obviously not. It's an average. So some of them are moving much faster, some of them are moving much slower, but when she records the temperature of this, it's the average of all of that. It's the average thermal energy. It's the average thermal energy. And it's important that you understand it's a measurement. The temperature is not something that you just have. It's a measurement of the thermal energy. Hi, Mr. Leverchek. How excited are you guys to do some math?
I love math.
Yay, good, okay. Do you have questions about any of this before I erase it? What if you're not done writing it down? What can you do? You watch the video, good. Okay, I'm erasing this at this time. Please write down, we're going to talk today now about the mathematics of thermal energy. So please write down thermodynamics math would be a good section heading here. Thermodynamics math. We're going to have one, I would say pretty simple equation, but you can be the judge of that for yourself. One pretty simple equation, which you may have already done on your chapter review if you were working on that yesterday. Thermodynamics math. The general and basic equation for thermodynamics is Q equals mc delta T. The way you can remember this is Q equals m cat. This is not the letter A. Is this the letter A?
No.
This is not. This is delta. But it kind of looks enough like the A that if you remember Q equals m cat, you might remember the correct formula. Where Q is thermal energy. Define thermal energy for me again, someone. Where you raise your hand? No, raise your hand. Hunter. Yeah, the sum of kinetic and potential energy in a particle. The sum of the motion of the particle and the sum of the position of the particle is its thermal energy, and this is how we calculate it. Lowercase m is probably, as it always is, what? Mass, measured in What's the standard SI measurement for mass?
Kilograms.
Kilograms. Oops. That needs to be lowercase. This is one of the ugliest lowercase g's I've ever done. Capital C is something we haven't talked about yet, but it's specific heat, which is measured in joules per kilogram Kelvin or joules per kilogram degrees Celsius. And either of those are fine. Why? Do you know anything about Kelvin measurements? We'll talk more about them later in the year. But this is a temperature scale that has the same increments as Celsius, which is why either of these units is fine, has the same increments. The difference between 1 and 2 Kelvin is the same as the difference between 1 and 2 Celsius. They have the same increments, so we can use either for this part of the equation. But the Kelvin scale starts at absolute 0. You cannot have a temperature lower than absolute 0. And so what does that make special about the numbers in Kelvin? They can't be what? They can't be below 0. They can't be negative. Whereas even in Celsius, in fact, I don't know what it is outside right now, but it's probably a negative temperature Celsius. Remember that 0 in Celsius is freezing. It's probably below freezing outside, and so it's probably, I don't know, -5 or -10 Celsius outside right now. Why might it be beneficial for us mathematically if we use a scale where you can't have negative numbers? Well, for instance, in this one, if we get negative numbers, we might end up with a negative thermal energy. And that is not only buns, my friends, but that is straight breaking the laws of the universe. You can't have negative energy. So it ruins math if we use a negative temperature scale. So a lot of times we want to use Kelvin. And then delta, you remember what delta is?
Yes.
Change in, good. You see how this has come up a second time. There's a lot more instances of this, but we first learned delta when we did acceleration at the beginning of the year. Now it's not the beginning of the year anymore, and we're using it again. And then capital T, what's lowercase t? That's not this one, but what's lowercase t? Time. What's capital T? Temperature.
Oh, I got it.
And what do we measure temperature in? I just said kelvins or degrees Celsius. Why did I not put a unit for change in? Yeah, change in is not. It doesn't have a unit. That's not really. This is not even really a variable. It's just telling us that we're looking for what's another way we can write change in. So if change in temperature we can rewrite as, well, we had change in velocity before, and we could rewrite that as v sub f minus v sub naught. How could we write temperature, change in temperature? T sub f minus T sub naught. That is final temperature minus initial temperature. It's the difference in the temperatures. How the temperature changed. Okay, so if we have C measured in joules per kilogram degree Celsius or joules per kilogram Kelvin times Kelvin or degree Celsius times kilogram, what is our Q going to be measured in? Here's a hint, too. Yeah, joules. Does it make sense to measure energy in joules? Yeah, we've been doing that for the last 3 chapters. It does make sense to measure energy in joules. A wooden block has a mass of 20.0 kilograms and a specific heat of 1,700 joules per kilogram degrees Celsius. Find the change in thermal energy of the block as it warms from 15 degrees Celsius to 25 degrees Celsius. Did I just make this up, do you think? No, you could tell from what I was looking at and probably the way I was speaking that I was reading this from a book. This is a real problem, just like one you might have on the test. We're going to do it in a second, but first, specific heat is, we talk about specific heat as the amount of energy it takes to raise the temperature of an object. So something like water has a high specific heat. It takes a lot of energy to raise its temperature. Something like metal has a low specific heat. It doesn't take very much energy at all to raise its temperature. If you get your mom's cigarette lighter and you light it and you put a metal needle over it,
Oh, I've done that.
or you put a little cup of water over it, the needle will heat up much faster because it has a high thermal conductivity, and that's related to specific heat. So let's do this little problem together. Let's do it in a different color because I've just now realized that this one does not show up on the video pretty much at all.
Oh, no.
What's my first step? I'm on, by the way, 162 if you want to follow along on the problem.
Yeah, that's all right.
Aaron, you had your hand up. What's the equation? Q equals mc delta T. Next step. What might I sometimes have to do that you will have to do on your test? What might I sometimes have to do? Manipulate. Do I in this case? Well, let's read the problem. It said, find the change in thermal energy. What am I looking for here? Thermal energy. Thermal energy. So do I need to manipulate this? No. Next step then. Raise your hand if you know. What's the next step? Good job raising your hand, Gabe. Peyton. Substitute. Tell me what to write. Bring down the terms you don't know yet. So Q equals, and someone hopefully has their book. I'm going to call on Fate actually because he has his book out so we can actually see what I should write in. What do I write in, Fate?
20 kilograms.
20.0 kilograms. That's important.
Temperature sub F.
Well, wait, you skipped C first, sorry. Would you tell me what the specific heat is?
1,700
Joules per gram, sorry, kilogram degree Celsius. Oh, and I kind of ran out of room, so I'm just going to have to erase this. Okay, and the next one, well, you're right, T sub F minus T sub naught. So what was T sub F? Read this problem very carefully. It says, as it warms from 15 degrees Celsius to 25 degrees Celsius. What's T sub F? 25, the final temperature. It said to 25 degrees Celsius. So 25 degrees Celsius minus 15 degrees Celsius. I'm going to rewrite this again, carrying down my terms and subtracting this time. Q equals 20.0 kilograms times 1,700 joules per kilogram degrees Celsius times 10 degrees Celsius. Because as you know, 25 minus 15 is 10. Q equals, calculator time. She's typing in 20.0 times 1,700 times 10.
Equals
340,000 what? Well, no, don't say yet. It is right. But look, kilograms are on the bottom here, so they drop out. Degrees Celsius are on the bottom here, so they drop out. We're left with joules. What's a better way to write this? Q equals 340 kilojoules. I'm going to rectangle it, Gunnar, because I don't like when people circle it.
Oh, I love the circle though.
You're right. We should do a Kyla Vogel here real quick.
You have to cloud it.
Cloud it.
No, it can't look like that. No, it has to. You want me to do it?
I'm doing my best.
Well, I mean, it looks good. I didn't say that it looks like a cloud.
Thank you, Raven. That's what I was going for. It looks like teeth. It looks like a little pile of teeth. Okay. Okay. Last thing before we're done. Ready? And this is mostly vocab words, so I'm going to go pretty fast. There are three main ways that thermal energy can be transferred. What do we call the transfer of thermal energy? I'm going to say it again. What do we call the transfer of thermal energy? Heat. So there are three types of heat. Heat. Types of thermal energy transfer. Oh, sorry, that parenthesis should be there. What are they? Tell me them. They're vocab words. There are three of them. Fate, what's one? Radiation. Someone say another one. Conduction. Someone say another one.
Convection.
Convection.
And
That's it. There are three.
persuasion.
Radiation is where an object is emitting electromagnetic radiation into space
They use radiation
in the form of
for
heat.
X-rays.
Yeah. Okay.
That's not true, actually.
The heat is flowing out. Shh. The heat is flowing out away from the object. It's radiating, just like the radius of a circle is from the center out. It's radiating out from a central point, and the thermal energy is moving out from a central point. In conduction, what must be true of the objects? They must be,
Conductive.
what must they be doing? In this one, it could be just an outside, yeah, they must be touching objects. So I'm going to draw a little picture of soup, and here's a spoon. There's a spoon, and the spoon is touching the soup, isn't it? That's a weird way to phrase that for normal people, but it is touching the soup. And the heat from the soup is flowing into the spoon and up the little handle. Objects touching. In my example about putting my hand on the board, versus putting my hand on the cup of coffee, that was conduction. They were physically touching. The heat was flowing from one thing to another through physical touch. Let's go back to radiation for a second. Is there an object called a radiator? I can think of two objects called a radiator. What other? There's one behind Willie.
And it's like a kind of chemical.
And there's also one on a car. I'm just going to draw an old-timey car one because that's what I know how to draw. In both of these cases, heat, thermal energy, warm objects are inside of them, and it's radiating out from within them. The radiator is trying to keep the engine cool, right? The hot water from the engine is flowing within these little zigzags, and that's allowing the warmth from the water to flow out into the environment. It works much better when it's cold out. And in this one, the hot water is flowing within these pipes, and it's radiating out into the room.
And it's keeping it warm.
And it's keeping it warm. And what's convection then?
Convection is the beaker.
It's the beaker. I tried to draw. What might this be?
That's a beaker on top of a
This is
jar of jelly.
a hot plate. This beaker has what in it? Maybe water. And the convection takes the shape of these little circular paths of the flow of heat. So and this is very important. You should write this down. I'm going to say it because we're kind of running out of time, but I'm just going to say it. The hot water, in this case it's water, but a hot fluids flowing due to heat. The hot fluid gets less dense. Remember? The particles get further apart, don't they? You remember that from the beginning? The particles get further apart. That makes them less dense. And so, just like any less dense object, they float to the top. When they're at the top, what do? It's hot down here and cold up here. When they get to the top, what do? They cool down, get more dense, and sink back to the bottom. Where they get heated up, get less dense, and float back to the top. And that makes a little circle, and that's called convection.
So how come when I microwave my soup,
Yeah.
the top is hot and the bottom is cold?
Yeah, it shouldn't be, probably.
Because microwaves don't use convection, they use radiation.
Well, but the soup should still be convecting. I think if you just microwave it a little bit longer, it will start to do that. And it depends on where the magnet is. Some of them do. You're right. Maybe a bad microwave does have its little magnet on the top, and so maybe that's it. But that's why it's ineffective. That's why if you have this, I don't think people do this anymore, but if you have a bad buffet and there's just these heat lamps on top, then this is gravy, and there's nothing down here to keep it warm, the gravy gets hot up here, but it can't convect because it's already hot on the top. And so this stays ice cold. Bad gravy down here, and this just turns into like cake because it's getting baked. Just a nice thick skin of gravy you have to break through with the ladle, and then on the bottom it's just ice cold. Questions about thermodynamics? Your book, listen. In addition to the things we talked about, you need to know all of your vocab words. We didn't talk about insulators or conductors, but you need to know about them. We didn't talk about, that's it.